Greetings and salutations, my young Padawans. This is lesson 3.6, Quadratic Inequalities. So, real quickly, let's remind you how to graph a quadratic equation. We spent some time on this in class the other day, but this is a vertex form equation. So really quickly, I can identify the vertex of 3, 1. Again, that's h and k right here. So h and k. So 3, 1 puts the vertex right there. And then based upon that, if I wanted to, I could in fact create a table of values. And a table of values is really helpful for this problem. And if you then take these values and plug like 4, like we'll take this number 4 and plug it back into an equation. So 4 minus 3 is 1. 1 squared is 1. Times 2 is 2. Plus 1 is 3. So I can end up with the value of 4, 3. Because of symmetry, 2, 3 is also a point. I do the same thing with 5. I do 5 minus 3, I get 2. 2 squared is 4, times 2 is 8, plus 1 is 9. And again, because of symmetry, I can get that point. So, really quickly, I can plot some more points. Now, the other two aren't going to be on this graph. But I end up with my quadratic equation in vertex form. That looks like this. I know that was fast, folks. If you need to, go back in the previous video, and it will help you out to be able to graph this a little better. The lesson today is just going to be changing that equals sign to an inequality sign. So I want you to understand that when we graph this, nothing's really going to change. We're still going to identify the vertex the same way we did before. This one at -4, 3. Again, because it's in vertex form, I can do that pretty quickly. So -4, 3 puts my vertex right about there. And then if I want to, I can, of course, create my table of values from there, which looks like this. And then I'll plot these points. Now, before I connect the dots, this is where that inequality comes into play. So I need you to look at this inequality, and we need to remember that if you have a less than or a greater than sign, that will mean a solid line, like I do in this particular problem. So I can feel very confident that I can connect these line or these dots or these points. I can connect these points with a solid line. If it was just a less than or a greater than sign, I would use a dashed line, of course. But that's not what I have going on in this particular problem. But don't forget, when you're graphing inequalities, linear or quadratic, or for that matter, anything else, it matters whether you have a solid line or a dashed line. Okay, so now, just like we had in a linear equation, we're going to check. We're going to check which side we want to shade on. Because again, remember, with inequalities, we're going to shade. And with a quadratic inequality, it's basically going to be inside of the U or outside of the U. So, in order to do this, we're going to check a point. Now, I'm a big fan of checking the point 0, 0. I think 0, 0 is the easiest point to check, provided your equation does not go through the point 0, 0. So you can see that the point 0, 0 is right there. So we're going to check and say, does that satisfy the inequality or not? So let's look. And we're going to look at the inequality with the coordinate pair 0, 0 plugged in and see if it satisfies the inequality or not. So here I plugged in 0, 0. So 0 less than or equal to negative 0 plus 4 squared plus 3. Let's simplify that and see what we end up with. Let's see here. 0 plus 4 is 4. So I have 4 squared plus 3. 4 squared is 16. So I'll slam that negative sign in front of it. So I have negative 16 plus 3, which is in fact negative 13. So I'm down here to my final statement. 0 less than or equal to negative 13. So is that inequality true? And of course, no, it is not true. It is not true, therefore, this point does not work. This is a no. It doesn't work, which means none of my shading can occur on the side of the curve that has the coordinate pair 0, 0 on it. So that means I'm shading inside of this quadratic equation or inside the parabola. So we're going to shade inside the parabola. Let me do it better. Yeah, I like this marker. That's a nice marker. I'm spending way too much time shading. So again, don't forget, greater than, less than sign, we use a dashed line. Greater than or equal to is a solid line. And generally speaking, if our equations are in the form y less than or equal to or greater than or equal to, if it's a greater than or equal to, we're going to shade above the curve. And if we're less than or equal to, we generally shade below the curve. And again, it's got to be in that very specific form. Let's take a look at another problem. So this quadratic equation is in standard form. That doesn't mean we're going to do anything differently. We're still going to look at this as we did when we graphed a quadratic equation, so we'll find the vertex by using the opposite of b over 2a. So let's hear. The x value of the vertex is the opposite of b, so the opposite of -2 over 2 times -1. And that will give me, let's see, that's 2 over -2, which is -1 for the vertex. And then I'll take that value, and I'll take that -2, and I'll plug it back into my equation. So that's here, that'll give me -1 squared minus 2 times -1 plus 15. That's here, that's negative, and then -1 squared is 1. I got plus 2 plus 15. That gives me 16 as my coordinate pair. Okay, so my vertex is at -1 comma 16. Oh man, this graph is not going to work for me, is it? Okay, so let's fix the coordinate pairs here, and instead of counting by ones, we'll count by 5. So let me fix my graph, my coordinate graph over here. So that'll be 5. We'll make that 10. That'll be 15. So forget about that and that and that and that. But you know what? We'll still count these by ones. So that'll be 1, 2, and 3. I got -1, -2, -3. I have -5, -10, -15. I think that'll make it a little bit better for us. So we'll plot the coordinate pair -1, 16. That's about there, right there. And then we can come up with a table of values for the rest of it. So let's do a table of values really quick by, again, we'll put that -1, 16 in the middle. And we'll number up, we'll number down, and we'll fill in this table of values, again, by taking these values and plugging them in to the original equation. And then I'll use that idea of symmetry to help me figure out the other coordinate pairs. So let me plot these real quick. All right, so I plotted my coordinate pairs over here on the graph, and now it's up to doing the shading and figuring out if this is a solid or a dashed line. Let's see here, it's a greater than sign, which means I'm going to connect this with a dashed line. So a nice dashed line is going to be what I'm going to use for this quadratic equation. I'm going to do my best to make it look like that U. I'll put little arrows on the end. And this is a greater than sign. So again, if you want to, you can always check a coordinate pair. I like to check 0, 0 again. So we can check 0, 0 and say, does 0, 0 work? Real quick, 0 greater than -0 squared minus 2 times 0 plus 15. Well, that's basically 0 greater than positive 15. That's not a true statement, so that point does not work, which means once again, I am shading on the other side of my equation, which means I'm shading all the way outside of this U in this particular case, because 0, 0 does not satisfy the inequality. Again, I'm having way too much fun shading my equation. Man, what if we had a system of inequalities? No different. We just shade each one of these things individually, or we graph them individually. So I'm going to do that right now. I'm going to kind of skip going over this since we just practiced all that graphing, and I'm just going to show you what the two equations look like on this graph, and then we'll talk. So here's that top equation, y less than -x squared plus 3. Now I'm going to take that second one, that second equation, y greater than or equal to x squared plus 2x minus 3, and I'm going to plot it on the exact same coordinate plane. Here's what it looks like. So there's the second inequality that's shaded. Now we're looking for that intersection area. So we're really looking for this area of intersection where the two shaded regions overlap. And any point that is in this shaded region is going to satisfy both of these inequalities. And that is where my solution actually lies, in this region, that overlapped region. All right, so we're at the point where I'd like you to pause the video right now. I'd like you to try to graph these and make sure that you get the graphs correct. And of course, I will show you the answers here on the next screen. So pause the video right now and try these out. I use Desmos, but your graph should look very similar to this. Notice that the vertex is at 1, -9. The line is solid, and you have shaded in between the U. Here's number 2. Notice the vertex is at the coordinate pair 1, 5. It is a dashed line, and you're shading outside of the U. And for this system of inequalities, please notice that the red line here, is this top curve, y less than or equal to -x squared. and it's a solid line, and we're shading in between. And then we have this dashed line for the second equation. It's a blue dashed line. And the solution is actually this overlapped region right here in between that overlaps. Well, what if we don't want to graph? What if we want to just solve an inequality because there's only one variable? So here's the problem, x squared plus 4x minus 32. And what if we want to figure out and solve this inequality? Where is this quadratic greater than 0? Well, the good news is we can actually solve this just the same as we would a regular quadratic equation. What I mean is, look at the equation version where we drop the inequality and pretend that it's not there and just set it equal to 0. Then we have this quadratic equation, which we can solve, again, using any method we had previously talked about. Maybe that's using the quadratic formula, or in this case, factoring. The pair of numbers that multiplies together to give me negative 32, but adds together to give me positive 4 is x plus 8 and x minus 4. So when we solve that by setting each one of the factors equal to 0, we'll end up with two solutions of x equals negative 8 and x is equal to positive 4. Now, here's the deal. When I'm looking at this kind of gives me like the different regions. It's kind of like a different breakdown of the regions of the graph. So if you think about it in terms of x-intercepts, one of the x-intercepts is negative 8. The other will be 4. And if you have a quadratic equation, that's going to be where this quadratic changes from positive to negative. If you looked at a graph, I could convince you that that was true. But instead, here's what I'm going to do. I'm going to put that negative 8 and that 4 over there on my number line. And then in each one of the regions, I'm going to pick a number. So I'm going to pick a number that's down there that's lower than negative 8. I don't know. Let's talk about x equals negative 10. How about negative 10? Negative 10 is less than 8. And then I'm going to pick a region or a number here that's between negative 8 and 4 in that area. Say x equals 0. X equals 0 is between negative 8 and 4. And then I'm going to pick a number that's greater than 4. I don't know. How about 5? Why not? And what I'm going to do is, just like I tested a coordinate pair on the graph of my inequality, I'm going to test this single x value in my original inequality. So I'm going to take this negative 10 and I'm going to plug it back into my original equation. So that's negative 10 squared plus 4 times negative 10 minus 32, and I'm going to see, is that greater than 0? Let's hear it. Negative 10 squared is 100. 4 times negative 10 is negative 40 minus 32. And when I did that math, I'd get 28 greater than 0. That is, in fact, a true statement. Therefore, for that section of my inequality, this is true. It is a true statement. Let's check out x equals 0. Okay, so x equals 0. So that's 0 squared plus 4 times 0 minus 32. Is that greater than 0? Well, let's hear 0 squared is 0, 4 times 0 is 0, so I really end up with negative 32 greater than 0. And that is not a true statement. Negative 32 is in fact not greater than 0, so I know that this section doesn't work. And finally, let's take a look at x equals 5. I'm going to need to go down here. So I'll do x equals 5, and I'll plug that into my equation. So that's 5 squared plus 4 times 5 minus 32. Is that greater than 0? Let's see here. So that's 25 plus 20 minus 32. 25 plus 20 is 45 minus 32. That gives me 13. Is 13 greater than 0? Yes, it is. So that, in fact, does work. So what is the solution to this inequality? The solution to that inequality is the sections of this region up here that make this work. So I look at this region. What is that region? Well, those are values that are less than negative 8. So my solution has to include values where x is less than negative 8. And it's not equal to because the inequality that we started with wasn't equal to. This inequality is just a greater than sign. So notice there's no equal to. And the second region is this region up here. So it's this region up here. So what is that? So that's when x is greater than 4. So my two solutions, when x is less than negative 8, that's this region here. And when x is greater than 4, which is this region here. Let's look at another one. 3x squared minus x minus 5, less than or equal to 0. Even if I ignore that less than 0, I have a quadratic equation here that's not factorable. So I'm going to have to figure out a different method to solve this. Why not the quadratic formula? Okay, so let's see. That is the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a. Okay, let's see here. So that'll give me 1 plus or minus the square root of 1, 4 times 3 times, well, let's see here. So that'll just give me 61 underneath of that when it's all said and done over 6. Okay, 61 can't be simplified down, so that means my two answers would be 1 plus the square root of 61 over 6 and 1 minus the square root of 61 over 6. So that's exactly what I'm going to do when I'm going to split my region up. 1 plus the square root of 61 over 6 and 1, well, wait a minute, hold on a second. This would have to be 1 minus because that's smaller, and this would be 1 plus the square root of 61 over 6. But I don't know about you, but I don't know what that is. 1 minus the square root of 61 over 6? I have no idea where that is on a number line. So it's going to be really hard for me to pick numbers that go up in each one of these regions if I don't know what these numbers are. So what I'll do is I'll pull out my calculator. And my calculator can help me with a decimal equivalent. So I know 1 minus the square root of 61. That's approximately negative 1.47. I'm sorry. 1.14. And I know that 1 plus the square root of 61 over 7, that is approximately 1.47. So this will help me be able to figure out better numbers that I can test in each one of my intervals. So like, for example, here I might pick x equals negative 2. I like x equals 0 in that region. And here, how about x is equal to positive 2? And when I test those values, I'll find that this doesn't work, this does work, and this does not work. So my answer here is going to be whatever is in this region right here, in between my two values. So my solution to this inequality is going to be exactly those values, the values that are between 1 plus the square root of 61 over 6 and 1 minus the square root of 61 over 6. All right, so now it's time for you to try these 3 problems. So go ahead, pause the video right now and try and work out these 3 inequalities. Good luck. Pause the video. We'll go over them here momentarily. Okay, so number 4. So again, the first thing that I'm going to do is I'm going to rewrite this. I'm going to ignore the inequality, and I'm going to make sure it's set equal to 0 so that I can solve this using either factoring or the quadratic formula. Since this is in fact factorable, let's see here. It would be plus 2, and then that would be minus 1 equals 0. I'd end up with the values of 1/2 and negative 2. You might have to factor that a little bit more using Xbox or something like that, but I'm telling you it'll factor down to be 2x minus 1 times x plus 2. So now we'll put these on a number line. We'll pick values in between. So for example, let's here, I'll pick x equals 0, like x equals, I don't know, negative 5, and how about x equals 1? That's in those regions, and we'll test those values out. When you do, you'll find that this region doesn't work, this one does, and this one does not. So my solution will be everything between my numbers. So between negative 2, less than or equal to x, which is less than or equal to 1/2. Same thing with this problem. Because this one isn't factorable, I'm going to have to use the quadratic formula. So I'll fill in my numbers, and the quadratic formula will look like this. And it simplifies down to 4 plus or minus the square root of 28 over negative 6. I can furthermore simplify my radical. I get 2 square roots of 7 over negative 6. And that will allow me to get the final x values of 2 plus or minus the square root of 7 over negative 3. And I'll put those on my number line to test them out. But before I do that, it might be a good idea to see what they actually are equal to numerically. So 2 plus the square root of 7 over negative 3 is negative 1.5486. Some more decimals. And 2 minus the square root of 7 over negative 3 is approximately, waiting on the calculator, 0.2152. So on and so forth. So on the number line, that would put That would put 2 plus the square root of 7 over 3, negative 3 here, and 2 minus the square root of 7 over negative 3 here. And then I can pick my values in each one of these regions. So let's see here. This guy's about, so like this would maybe x equals negative 3. I could still pick 0 here, that's nice, and maybe x equals 1 there. And I'll test these values out. I'll find that this region works, this one does not, and this region does. So my solution will be this region here. So x less than 2 plus the square root of 7 over negative 3, and this region up here, or x greater than 2 minus the square root of 7 over negative 3. Finally, 2x squared plus 2x is greater than negative 5. I'm going to set it equal to 0 and solve this quadratic. It is in fact factorable, so I can easily come up with the answers of 1/2 and negative 2. I'll put those over here on my number line. Negative 2 is here, negative 1/2 is here. I'll pick values in each one of the region, like, I don't know, negative 5. Ooh, how about negative 1 here, because I'm going to pick 0 for up there. When I plug values into test, I will find this will work, this will not, and this will work. So my answers is this region here, which is when x is less than negative 2, or this region up here, when x is greater than negative 1/2. Negative 1/2. All right, folks, those are the answers to these problems. Good luck with your classwork.